Okay, we're going to continue on here, chapter 15, a new chapter. That's good. So, chapter 15, as we talked about last time, not a big chapter, but a few important things in there. And we're talking about really two different types of Ks, KSP, and towards the end there, we will talk about KF. We started last time really talking about KSP, which is the solubility product. And basically, the KSP, as we talked about last time, is really for things that are technically kind of insoluble. So these are really for all these things that you look at solubility rules, and they are basically going to be solids. And with that being said, that means that when we do sort of write these equations for what's going on here, it has a very typical sort of setup, and that setup is our solid sort of insoluble guys on the reactant side, and our aqueous ions are on the product side. So we have our aqueous ions on this side and our solid on that side. And as we talked about last time, even though something is technically insoluble, there will still be a little bit of it that will break apart into ions. So, even though, again, based on the solubility rules, it says this thing is always going to be sort of insoluble and you always get a solid. Even with that being said, it still is able to set up this equilibrium. And just a little bit of it, for example, will sort of break apart into ions, which is why we do kind of consider it to be insoluble overall, because most of it's a solid, but we do have a little bit that will break apart. So we can write a KSP for this, and we looked at, say, silver chloride, for example, which based on solubility rules tells us it's going to be insoluble, and we would have this sort of reaction here. And again, we have our ions on our product side and our reactants, there's our solid. So typically speaking, we do write our KSP like a normal equilibrium expression, which is products over reactants. But in this case, since pretty much all the time the reactants are going to be solids, you pretty much don't put the solids in or the reactants in. So pretty much every time it's just going to really be the products in this case. We still do the same thing as any other normal sort of equilibrium. If we do have a coefficient, we do have to sort of take that into account and use that as the exponent when we do write our KSP. So this KSP would be the concentration of silver times concentration of chloride. And when we do problems such as this, there's really kind of two types of problems that we typically come across. And those two types of problems is either one where they give you the KSP value, or that's the only thing that you have. Maybe you have to look it up in a table. And in that situation, you should do an ice table. And like we did, I think, on the very last example there, ice table is very similar to what we've done before. As we talked about, we use a different letter in these ice tables, and that letter is S. And the S does stand for the molar solubility, which is basically the molarity. We also have sometimes just the solubility given in more of a usable type of unit, which is something like grams per liter. So you know how many grams you could dissolve in, say, a liter of water or something like that. Um, in this case, we would come down, we would have our S's. Just like normal, we would take these S's into our KSP expression, and we would solve for S. When we do solve for S, that is the molar solubility. Is technically equivalent, obviously, to like the X values that we get in our normal ice tables. So in the case of something like silver and chloride, because at equilibrium they do equal S, that would also be the concentration of the silver ions and the concentration of the chloride ions in solution. And when we do solve for S, it is also typically the concentration or the molar solubility of the whole thing together. So typically when you get that S value, that's really the molar solubility of the entire compound together, which, as we talked about, if you wanted to go from molar solubility, which is moles per liter, to kind of grams per liter, it is the molar mass there that is the guy that ties those guys together. To do that conversion, as the moles here would cancel out and giving us grams per liter. Now, clearly, if you did have some coefficients here, you would have to take that into account with your S's, and that might not be when you get S, obviously, what the concentration of the ions would be at equilibrium if you did have some numbers that were present. The other type of problem is one where they just give you the sort of solubility of the product or the solubility of the ionic compound. They may give it to you in a wide variety of sort of units, whatever units they may give it to you in. But ultimately, if they do that, you could also do an ice table and kind of put your things in. But you do want to make sure that ultimately, whatever sort of solubility they give it to you in, you kind of get it to the molar solubility or the S. And once you do that, you can go into the KSP expression and actually solve for the KSP. Any questions on any of those things? Now, since these things are typically insoluble and things that are typically thought of as being solids, we typically find KSP values to be very, very small values because, they're mainly insoluble and staying together. Any questions on any of that there? All right, so I think we finished up on an example there where we saw that, for example, silver chloride, the molar solubility, I think, was something like the grams per liter, was something like 0.002 grams per liter or something like that, that you would be able to dissolve silver chloride in. So as we know, that is a very, very small amount, which is why we think of like silver chloride as being insoluble, because you definitely are not dissolving very much there. All right, then let us do the next example that we have. Once again, sorry about the spacing here. What is the concentration of aluminum ions in a saturated solution of aluminum hydroxide? The KSP here is 2 times 10 to the minus 32. So give it a go, see what you come up with here. Okay, let's take a look. So once again, a couple things as we talked about last time that just in case you don't know, some solubility type situations. Since there is a KSP for aluminum hydroxide, you could safely assume that that's going to be a solid in this case. Again, solids always go on the reactant side, but it will break apart into its ions, which would be aluminum 3 and 3 hydroxides here. We could write our KSP expression for this, which again will be just our products as our reactants are solids. So we have an aluminum, we have hydroxide, and again, we do need to make sure that we cube it there because of the coefficient, again, that we have here. So we want to make sure we do that. That would equal the KSP that they gave us, which was 2 times 10 to the minus 32. So in this case, since we are only given the KSP as we were just talking about, we want to definitely roll with an ice table. So 0 and 0. Change will be plus S plus 3S. And that means that when we reach equilibrium here, we have S and 3S. Any questions on the ice table here? Like normal, then we're going to go into our KSP expression. So that is going to get us something that's going to get us there. S times 3S cubed will equal our KSP value of 2 times 10 to the minus 32. So in this case here, we will end up with 27 S to the 4th is equal to 2 times 10 to the minus 32. I would say that probably a majority of the people will cube the S, but never do anything with the number. So remember, you got to also cube the number there. So 3 times 3 times 3 will get you there. So it's a very common mistake. People kind of just do the letter without doing the number part of it. So make sure you don't miss that part. We'll divide it by our 27 there, and that'll give us S to the 4th is equal to 7.407 times 10 to the minus 34. We're actually going to take the 4th root here of both sides. And when you do that there, you will end up with a number, perhaps. You'll end up with 5 we'll call it about 5.2 times 10 to the minus 9 in this particular case. By the way, if you're not sure how to take the fourth root, you may have a button on your calculator like that you can hit 4 and then that button to do it. If you don't have any of those buttons, this is a place where you could use like the caret button if you have, and do parentheses 1 divided by 4, and that will take the fourth root of it. 1 divided by 3 will take the third root of it. 1 divided by 2 will take the square root of it. So that's a way that you can punch it in if you're not sure how to do that. This particular case here. Question on that there. Now, to answer the question here, we're looking for the concentration of aluminum at equilibrium. So that does equal S, and that would be basically the molar solubility, or the molar solubility of the whole thing, but it would also be the concentration. By the way, also, if your calculator was not in scientific notation, you might have got a bunch of zeros and a 5 at the end of your calculator, if it's not in scientific notation. So again, you might get that answer. Remember, though, if we wanted hydroxide's concentration at equilibrium, it actually equals 3 times S. So if we wanted the hydroxide, we would actually have to do 3S, which would be 3 times 5.2 to the minus 9. And that's going to give us something like 1.6 times 10 to the minus 8 molar. And once again, as I was mentioning a second ago, if we wanted the molar solubility of this guy, that would be the value of S. As if we took that S value and it was a 1-to-1 relationship here. If we took this, it's a 1-to-3 relationship, so it becomes the same number. So again, when you solve for S, it is the molar solubility pretty much of the entire thing. Any questions on any of those parts there? Oh. So let's talk about then, can we use KSP values to compare solubilities of different ionic compounds? And the answer is yes and no. So the answer is it depends really on the situation of what you're comparing. So if you take, say, 3 salts, for example, like they have here, silver iodide, copper 1 iodide, and a little calcium sulfate. Each of these ionic guys, when they break apart, will break apart into the same number of ions. So this guy will give us a silver and an iodide. This guy here will give us a copper and an iodide. And this guy here will give us a calcium and a sulfate. And what we mean by the same number of ions is pretty much that. I got 1 and 2 ions there. I have 2 ions there, and I have 2 ions here. So they each break apart into 2 ions, which means in that particular situation, you can use the KSP values to directly compare between the 2 salts, which one should be more soluble or which one should be less soluble, or if you want to think about that aspect of it. And what we would do is the larger the KSP value, it should be the more soluble it is. And that goes back to the idea of a large K value. So if we have a large K value, that means that we should have mainly products. And if we have mainly products in all these reactions, that is our aqueous ions, which means it's more soluble. The smaller the KSP value, it would mean we have more reactants, which means the thing is staying together and it should be more insoluble in that case. So if you want to compare the solubilities of 2 ionic sort of salts, you can do so, but you could only compare if they break apart into the same number of ions. And that's because mathematically speaking, if you were going to calculate the molar solubility of each of these things, it would be pretty much the same calculation. So you have the exact same calculation and comparison. So in this case, if we looked up the KSP values for calcium sulfate, copper 1 iodide, and silver iodide, we would see that the calcium sulfate would have the larger KSP value, and would be more soluble. The silver iodide would have the lower KSP value and be less soluble. Now, what happens in a situation where we have salts that do not break apart into the same number of ions? So here we have copper 2 sulfide, and this guy, when he breaks apart, will break apart into a copper 2 and a sulfide. Silver sulfide here will break apart into a couple of silvers and a sulfide. And a little bismuth here will break apart into a couple of BIs and 3 of the sulfides. So in this case, all these guys break apart into different numbers of ions. And that means if we looked at just the KSP value, which is this column right here, we just took a look at the actual KSP values for each of these, we would actually see that it is the copper 2 sulfide that has the larger KSP value. And based on that, we would predict that this guy would be the most soluble, and this guy has the lowest KSP value, which means we would predict that this guy would be the least soluble if we just went by KSP values. And the reason we cannot go by KSP values in this case is because they do break apart into different numbers of ions. And what we actually see when you do an ice table and actually calculate like the molar solubility of everybody, we actually see the opposite trend in these guys. It is actually the bottom guy here that is the most soluble based on the calculation. And it's actually the top guy that is the least soluble. So in a situation where you are wanting to compare solubilities of salts that break apart into different numbers of ions, because really the math part of it is different when you do that, you do actually have to carry out the calculation and calculate the molar solubility of each of those and then do the comparison. So that's why the answer is yes and no. Yes, in the sense you can use the KSP value if everybody's the same number of ions, breaks apart into the same number of ions, and you can compare solubility. If they do not, you do have to do the calculation for each of them and then compare the solubility. Any questions on that there? All right, so we also talked about the idea of solubility rules not being always 100% correct for every situation. So as we talked about last time, there are a number of things that can affect the solubility of a particular substance. And we're going to talk about those things that, again, even though maybe solubility rules say it should be a solid, it may not actually occur and why that may happen. So one of the first things that can affect the solubility of a substance is actually the same thing that we saw when we talked about buffers, which is common ion. And the common ion effect, as we saw with buffers, will basically keep the weak acid or weak base together, right? It prevents it from dissociating completely. And that is the same idea that happens here in sort of our KSP type of situation. And it really is basically, if you just think about how these reactions are set up, you again have solid on the left and our aqueous ions on the right, which means if you have a common ion, the only place in the equation it could end up is on the product side, right? And if you have a common ion that's going to be on the product side, that would be based on Le Chatelier's principle, adding more products, which means we should expect the equilibrium to actually shift away from it to our solid. So much like what we see with buffers, if you have a common ion, it will actually decrease the solubility of a salt because it's going to push the salt back together based on Le Chatelier's principle, and you actually see a lower solubility when you have that common ion present. So as an example, let's take a look at silver bromide, and that's the KSP for silver bromide here. And if we wanted to just calculate the solubility of silver bromide in pure water, we would do our normal sort of ice table. So we'll take our silver bromide, which will break apart into a silver ion and a bromide ion. And again, here we only have the KSP, so we'll do our ice table. It's going to be 0 and 0, change plus S and plus S. That means at equilibrium, we'll have S and S. At this point, we could go into our KSP, which should be the silver concentration times the bromide. And putting our values in here will give us basically S squared is equal to 7.7 times 10 to the minus 13, which is our KSP value that was given to us. We're going to square root both sides. And if we square root both sides there, that is going to get us a molar solubility of, we'll call it 8.8 times 10 to the minus 7, which would be our molar solubility in this case. And if we wanted like our solubility in grams per liter, we could get the molar mass here, which would be like 107.9 plus 7990. It's about 187.8. So if we took our 8.8 times 10 to the minus 7 moles per liter, times it by the molar mass of 187.8 grams per mole, that would tell us that we are looking at something like, bless you, 0.000165 grams per liter as the solubility in grams per liter, which clearly is not a lot to begin with, which is why we again consider silver bromide to be very insoluble. Basically, in water, you could get 0.0002 grams of it to dissolve, right? Which is not very much in 1,000 milliliters of water. So that's a very, very small amount. Now, let's talk about what happens if we don't have silver bromide, say in pure water, but we also add some sodium bromide to it. So in B here, we're going to add some sodium bromide to it, and we're going to still get the silver bromide as the only thing that's going to set up our equilibrium. But now we are adding 0.001 molar sodium bromide in there, which is a salt that will break apart into a sodium ion and a bromide ion. And as you could probably imagine, it is the bromide ion here that is our common ion. And the deal here is where it affects is actually much like in sort of buffers. If you're going to do an ice table, it affects the right-hand side. We do have an initial concentration of bromide in this case being supplied by the sodium bromide. So this guy would be 0, but our bromide here would be 0.001 as it is being supplied by our sodium bromide in this particular case. Now, the rest of the table is going to be very similar here. So plus S and plus S. That means when we reach equilibrium, we have S and 0.001 plus S. Let's see. Any questions on that so far? So much like what we did before, I'm just going to erase some of that there so I got somewhere to write. We're going to go into our equilibrium expression. And when we do that in this particular case, we will get S times 0.001 plus S is equal to 7.7 times 10 to the minus 13. So again, just going into our KSP. We can do here what we've done previous type of situations, which is it's a pretty small K value, which means I'm going to assume XS is equal to 0 here. And just like when we assume X is equal to 0, we can't get rid of all of them. So it's just going to be the one you're going to add it to. And if you do that, that will get you S times 0.001 is equal to 7.7 times 10 to the minus 13. We're going to divide basically 7.7 to the minus 13 divided by 0.01, 2 zeros, and that's going to give us an S of 7.7 times 10 to the minus 10. We should check it like normal, but I would say probably with KSPs, you're going to be fairly safe. because they're very, very small values to begin with. And if you do check it, it's like not even near like 0.00007%. So it's check it's in this case. Now coming back here, that is again going to be our molar solubility of our compound. And we wanted to sort of compare apples to apples here. We could also convert that into grams per liter as well by using the molar mass. That's going to give us 187.8 grams per mole. And if we take that, we get something like 1.45 times 10 2, 3, 4, minus 7, if I counted the zeros right, grams per liter in this case. All right, so we can compare really either ones here. We could compare the molar solubilities and which one is more soluble. In this case, it is the one in water, right? So negative exponent, smaller number is a larger number. So, and we also see definitely here that's only like 4 places, and that's to the -7, also more soluble in water. So one of the things that can affect the solubility of something is the presence of a common ion. It's really still the Le Chatelier's principle, which will shift it back to the solid side and keep it together. Any questions on that calculation there? In either case, not very much is dissolving in either situation. All right, so why don't you try one here? The KSP of silver chromate is 9 times 10 to the -12. What would be the solubility of this compound in a solution that was already 0.1 molar potassium chromate? We could do the molar solubility here is good. Okay, look here. Once again, we're going to have our KSP for this guy here. So that is definitely the one that's going to set up our equilibrium. And we know it's going to be a solid because there's KSP with it. We want to make sure we break it apart correctly. So we do get a couple of silvers and a chromate in this case. That is going to give us a KSP expression here of silver, which again, we do need to square it, times the concentration of our chromate. And again, we're squaring it because of the 2 that is there. We were given just KSP value here, so we're going to do our ice table. But before we do, we have this in with some potassium chromate, which is K2CrO4. And that is going to break apart into 2 potassiums and a chromate. And once again here, our common ion is obviously going to be our chromate. So because concentration of the whole thing is 0.1 molar, it is a 1-to-1 relationship between that and chromate. That means chromate's concentration is also 0.1, which is basically what we need here for our ice table. So that's going to be 0. And again, if we do not have the 0.1 here, we're really not doing the common ion problem, right? We're just doing a regular KSP type problem if you zeroed at that point. Any questions on that there? Now, change here plus again 2s because of the 2 and plus s in this case. We do want to take that down and we will end up with 2s 0.1 plus s. Like normal, we're going to now go into our KSP expression, and that's going to get us here 2s. And once again, we still need to square it. And that again is, as I talked about last time, something people sometimes mess up on. They're like, well, I squared it. But I also need to multiply it by 2 or multiply by 2. I still have to square it. So again, sometimes doing the ice table, kind of seeing it out there kind of helps you hopefully not forget to do it. 0.1 plus s is going to equal, looks like 9 to the -12 in this case. Just like previously, I'm going to assume xs is equal to 0. And once again, it's just going to be that s. That's going to give me actually 4s squared, as I'm not going to forget to square the number as well. Going to give me 9.0 times 10 to the minus 12. If we take our 4 times 0.1, going to give us 0.4 s squared is equal to 9 times 10 to the minus 12. I'm going to divide that to the other side. I'm then going to square root it afterwards. And that will get us 9 to the minus 12 divided by 0.4. And also take a little square root action. Will get us perhaps something like 4.7 times 10 to the minus 6. Any questions on that there? That again, as I mentioned before, really will be the molar solubility here of our silver chromate. We also can check it like we did previously, and you're not even near 0.1%. So again, the check is good on it. That means that this here would be our molar solubility. And obviously, if we were looking for grams per liter, we could use the molar mass to calculate that. In this case, though, if I was looking for what the concentration of silver was at equilibrium, I would need to take 2 times that number I got for S. And if I wanted the concentration of chromate at that point, I would need to take 0.1 plus that number, which is still 0.1. The amount of chromate is really high, are basically the same because you added it, right? So this is a common ion, so that's why it's basically the same as what was there. Any questions on common ion and solubility? So common ion typically will suppress the salt from breaking apart and decrease the solubility of it. Let's then talk about another important aspect of what affects solubility, and that's actually pH and solubility. So pH plays in a really important role in terms of the solubility of a lot of things, especially things where there's hydroxide or H plus sort of involved, sort of acid base type situations. So the presence of the common ion, as we just saw, does decrease the solubility. We have insoluble bases will dissolve in acidic solutions, and insoluble acids will dissolve in basic solutions. So for example, let's take this equilibrium here, and we take some magnesium hydroxide where the KSP is going to be our magnesium, and our hydroxide here squared equals 1.2 times 10 to the minus 11. So if we ran through our sort of ice table here to figure out the solubility of everybody that's going on, we would do our normal calculation like we've been doing here. And initially, 0 and 0, change plus S plus 2S. That means at equilibrium, S and 2S. Putting that into our KSP expression, that's going to give me S times 2S that's squared is equal to 1.2 times 10 to the minus 11. That is going to give me something like 4S cubed is equal to 1.2 times 10 to the minus 11. I'm going to divide by the 4 and take the cube root of it. So we're going to divide by the 4. And then we're going to, bless you, take the cube root of it. So we'll take 1.2 to the minus 11 divided by 4, and a little cube root action happening there. And if we do that, we will get an S value here of like 1.44 times 10 to the minus 4. Now, that is the molar solubility of this compound. Now, in terms of pH, for example, what here would be important in terms of pH? It would be the hydroxide concentration, right? So by figuring out the molar solubility, we could also figure out what would be the concentration of hydroxide in that solution at equilibrium. So if we wanted the concentration of hydroxide at equilibrium, it would be 2 times S, which would be 2 times 1.44 times 10 to the minus 4. And if I do that there, that's going to give me hydroxide concentration of 2.88 times 10 to the minus 4. That's going to allow me to calculate the pOH minus the log of 2.88 times 10 to the minus 4. Do a little minus the log action there. That's going to give me a 3.54 pOH. If I then subtract 14 from it, that means that the pH here would be 14 minus 3.54. That's a 1046 pH. So from using our solubility information in this case, we were actually able to calculate the baseline pH of the solution, and it would be basic as we would expect since it is magnesium hydroxide and it is hydroxide. And it has a pH basically of 10.46. So first off, any questions on that calculation there? So here, obviously, you can use it to figure out, why is this important? So let's talk about it. Let's say that I decided I wanted to lower the pH here. I want to lower the pH below 10.46. So if I wanted to lower this pH below 10.46, the way I would typically lower a pH is, would I add an acid or base to it? I would add an acid, all right? And when we add an acid, that means that we are essentially adding H plus, right? It's basically what we're adding. And if I added H plus to this equilibrium here, what would happen? Is there any H plus in that equilibrium? There is not, right? There's no H plus, H3O plus. Is there anything that H plus would react with in that equilibrium? H plus and OH minus make water. Yes, the H plus and the OH minus will make water. That will essentially do what? That will essentially remove hydroxide, right, from this equilibrium. And when it removes hydroxide from this equilibrium, Le Chatelier's principle says it should shift which way? It should shift towards the side you removed it, right? Would that increase or decrease the solubility here? It would increase it, right? Because it's shifting to the side that has ions in it, right? So by lowering the pH, we will cause this equilibrium actually to shift to the right because we will essentially be removing hydroxide ions by adding H plus, which will make water, not H2, it will make water. And that will cause the equilibrium to shift to the right. And it will cause the solubility to increase. By the way, would I need to get it to be an acidic pH to see that happen? No, I would just need to get it lower than what pH? 10.46, which is why knowing that number is important because frankly, you just need to drop it below 10.46 and you will start to see actually the solids start to dissolve more. Still basic. You can even keep it in basic and you will actually see how fairly good. I mean, if you drop that pH to even 9, you would see a fairly good amount of it start to dissolve because it's much more acidic than it should be at that point. It's going to increase the solubility of it. Question on that there. That is what it means when it says insoluble bases will dissolve in acidic solutions. So if you just kind of lower the pH, you're going to cause that shift to the right. Now, let's say we had sort of the opposite and I decided that I wanted to increase the pH above 10.46. So if I wanted to increase the pH above 10.46, I'm most likely going to add a base, right? And when I add a base, that's basically adding more hydroxide. In this case, there is hydroxide in that reaction, right? Which means that would essentially be adding more products. And Le Chatelier's principle tells us it will then shift away from it, which shifts to the side that's going to be more solid in this case. So this will cause it to shift away and will decrease the solubility because you're basically forcing it back to the left there by adding more hydroxide. So if you took the pH above 10.46, which is where you have to kind of go above to actually see that happen, you would cause the solubility to decrease. So pH plays a really big role, especially where you have, some acids and bases sort of involved, to provide the right environment for perhaps things to precipitate out, perhaps things to not precipitate out and stay in solution. There's a bunch of experiments that you used to do years ago in this class, which is known as qualitative analysis, which is pretty much this idea. It's all about solubility. And one of the weirdest things that you do when you do those experiments, and it's weird sometimes to students as they're reading it, is it's like, make your solution acidic. And then the next sentence is make it basic. And then next sentence is make it acidic again. And it's like playing with the pH, going back and forth. It's weird things. And the reason you do that in those type of experiments is the idea is to keep certain ions in solution floating around and allow other ones to precipitate out. So you want the right sort of pH environment, for example, that will allow only certain ones, for example, to precipitate out until you're ready for them, and then keep the other ones kind of floating around in the solution. Any questions on pH and solubility? Now, the last thing that really does sort of, or one of the last things that really does affect sort of the solubility of something is the idea of concentration. And concentration plays a pretty big role in terms of whether or not, for example, again, you will see a precipitate actually form. Speaking of those type of experiments, sometimes when people do those experiments, they add a lot of reagents. And for example, every time you add a reagent, you're essentially diluting your sample because the reagents are basically water-based, right? So you're just adding more water and volume and you're doing dilutions. And there can come a point where perhaps, even though technically speaking, based on solubility rules, it says that these things should precipitate out and you should get a solid. It could come to a point where you don't have the right concentrations of those ions to come together to actually see the solid form. So again, this is where we can use our Q versus our KSP to compare whether or not a precipitation will occur. Again, if Q is greater than KSP, we would expect a precipitation to occur. If Q is less than KSP, then no precipitation will occur. A reminder that Q, once again, is calculated the same as the KSP. So again, you do basically products in this case. Also take the exponents and you compare them. So why don't you try that? If we mix together here 2 milliliters of 0.2 molar sodium hydroxide with 1 liter of calcium chloride, will a precipitate form? And by the way, you want to think about solubility rules as to what might be soluble. So if you think about sodium hydroxide, we basically have these 4 ions present. We could have sodium hydroxide, calcium chloride. And you want to think about any combination there that might make a solid. And as you should probably know, we will have something here, maybe. There we go. Calcium hydroxide is the only possibility, as sodium possibility would be to go to chloride, which is soluble, and then these guys would be our other option. So in this case, we really want to know, will we get calcium hydroxide forming? As that is probably our only sort of possibility of something that could form. We would also want to know the KSP for calcium hydroxide, and I'll give that to you, which is 8 times 10 to the minus 6. All right, so figure out whether or not we will get this calcium hydroxide to precipitate out. Okay, so let's take a look. So as it says here, we really want to calculate Q and compare it to the KSP. as our calcium hydroxide is our only option. So remember that Q is calculated the exact same way as we would calculate the KSP. We do want to make sure, though, that we are getting the correct concentrations here since we're mixing everybody together. We basically have sodium hydroxide, which is really a source of sodium ions and hydroxide ions in this case. And we also have calcium chloride, which is a source of calcium ions and chloride ions. So each of these guys are basically the sources of these guys, but we do want the concentration when they're mixed together. So that's a little M1V1 equals M2V2 action. In this case, for our sodium hydroxide, we have 2 milliliters of it and 0.2 molar. For our calcium chloride, I'm going to use 1,000 milliliters just to put the liters and milliliters, and 0.1 molar. So for our hydroxide in this case, it would be basically 2 milliliters times 0.2 molar divided by our total volume, which is again why I converted it to milliliters. So 102 milliliters. We'll do that. That will get us 2 times 0.2. You could also convert the other one to liters if you'd like to, but at some point you got to kind of get them probably in the same units. That's going to give us 3.99 times 10 to the minus 4 molar would be our hydroxide concentration. And it is a 1-to-1 relationship, right, between this and hydroxide, so we're all good. For our calcium, we'll do a similar calculation. We got 1,000 milliliters times our 0.1 molar divided by our total volume of 1,002 when they're mixed together. Milliliters will cancel in this case, and we will end up with like 9.98 times 10 to the minus 2 molar. Questions on that there? Now that we actually have the correct concentrations of these guys when they're mixed together, we're good to go into our Q in this case. Our Q will equal our calcium, which is 9.98 times 10 to the minus 2, times our hydroxide, 399 times 10 to the minus 4. Once again, we want to make sure we are also squaring that guy. And that's going to give us 3.99 to the minus 4 squared times 9.998 to the minus 2. Going to give us a Q of 1.6 times 10 to the minus 8 in this case. Questions on that there? At this point, we want to compare our Q value to our KSP value. And in this case, which one is bigger there? Q is actually going to be smaller, right, than the KSP value. KSP value is to the minus 6. This guy is to the minus 8. That means in this particular case, it goes opposite, right, towards the product side, which means that should be ions, and you should not get a precipitate in this case, right? So you will not get a precipitate to form. Any questions on that calculation there? So this is sort of, if you want to think about the third sort of effect that you could have on solubility. So what we've seen is pH, common ion, and the concentration of your ions all can have an effect on the solubility of something. So again, just because solubility rules say that you should see a precipitate, the environment, for example, is really important as well as to whether or not you would see a precipitate or not see a precipitate sort of form. Any questions on any of those things? Yeah. In terms of what affects it. There's pH, common ion, and concentration, yeah, of the ions. So other questions? And this is what I was talking about earlier, that sort of qualitative analysis experiment. Yeah, that's, like I said, a lot of reagents as you're doing those type of experiments. And it's very common people kind of over add because you don't really measure things out when you do those type of experiments, which is why it's called qualitative analysis. So you just take dropper bottles and drop, and sometimes people add too much and they're surprised at the end when their test doesn't work. They're supposed to see a precipitate and they don't see a precipitate. And sometimes it's due to the fact that they really over diluted it and the concentration of their ions are too small to actually see the precipitate form. All right. Let's then talk about another aspect of KSP, which can be really helpful when you're trying to do something like I was just mentioning there, that qualitative analysis sort of experiment. It's also sometimes called selective precipitation. So the idea here is maybe you have a lot of ions floating around in solution, and you want to only selectively take out a certain ion or a group of ions or something like that. So there is a way to use KSP to figure out, how you could kind of do that and maybe take out a certain ion, but leave the other one in solution. So for example, in this problem here, we have a beaker that has bromide ions floating around and chloride ions floating around. And we know based on our solubility rules that frankly, if we add silver to it, they should precipitate out. We should get silver chloride. We should get silver bromide. So we want to add silver to this to precipitate these guys out. Now, the problem is if you do not do this correctly, for example, you will get what's sort of in those pictures. And in those pictures, one of them is silver chloride and one of them is basically silver bromide. They're essentially both going to be like a white solid, which if you do not do this correctly, you can't just go like, I think this little white crystal is like the silver bromide. I think this one is like the silver chloride. You really would have no idea as to what you precipitated out, what might still be floating around in the solution. So this is where KSP can be very helpful to allow you to figure out how to correctly sort of precipitate these out. Now, our two options obviously is going to be silver bromide, which has a KSP value of 7.7 times 10 to the minus 13. And our other option would be silver chloride, which has a KSP value of 1.6 times 10 to the minus 10. So in this particular case, what we do know is the concentration of these ions is 0.02 molar floating around in there. So what we want to figure out is how much silver we need to add, like in the form of like silver nitrate or something like that, that will precipitate out only the bromide ions and leave the chloride still floating around. So the idea here is to add the silver that will then react with the bromide and precipitate out the bromide, but leave the chloride ions still floating around in the solution until we're kind of ready for them. So we can use our KSP expression to help us. So if we take our KSP expression, we know that the silver concentration times the bromide concentration here will equal our KSP of 7.7 times 10 to the minus 13. Now remember that we're looking to figure out how much silver to add. So we actually could solve for the silver concentration will equal 7.7 times 10 to the minus 13 divided by the concentration of bromide. In this particular case, we already know the concentration of bromide is 0.02. So we could put that in 7.7 times 10 to the minus 13 divided by 0.02. That is going to get us here. We'll call it 3.9 times 10 to the minus 11 molar. That number right there represents the minimum amount of silver that's needed to see what happened. To see silver bromide start to precipitate out. So that would be the minimum concentration of silver that's needed to actually see silver bromide start to precipitate out in this particular example. Now, we could also do a similar calculation for the silver chloride and figure out how much silver we would need to precipitate out the silver chloride. And if we do the same thing, we're going to take our KSP expression. It's going to be the silver concentration times the chloride concentration equals 1.6 times 10 to the minus 10. And again, that is our min concentration to see silver bromide precipitate. And again, we could solve for silver in this case, and that would be 1.6 times 10 to the minus 10 divided by our chloride concentration, which in this example is the same. So 1.6 times 10 to the minus 10 divided by 0.02 is going to tell us here, come here, 1.6 to the minus 10 divided by 0.02, 8 times 10 to the minus 9 molar. This number is the minimum concentration of silver needed to precipitate out silver chloride in this particular case. Any questions on that? What that means is which concentration of silver is higher, the one needed to precipitate out the silver chloride or the one to precipitate out the silver bromide? It is the one for silver chloride, and that's why the question asks to precipitate out the silver bromide first. So if you wanted to precipitate out all the silver bromide, you would need to get your silver concentration to be greater than 3.9 times 10 to the minus 11 molar, but you need to keep it less than 8.0 times 10 to the minus 9 molar, right? So if you get your silver concentration in this particular example up to 3.9 times 10 to the minus 11, you should start to see silver bromide coming out. So what you would see is white solid basically coming out in this case. And you can be fairly confident that it is the silver bromide because that's not enough silver to get the chloride to come out of solution. You could keep increasing the amount of silver if you wanted to, as long as you keep it less than 8 times 10 to the minus 9. And at some point, if you keep adding silver, you should hopefully stop seeing any solid come out. And at that point, you should probably be fairly confident to know that you precipitated out all the bromide. At that point, if you wanted to, you then could take your silver concentration and get it to 8 times 10 to the minus 9, and you once again should start to see some white solid come out. And at that point, you know that that solid should be the silver chloride, and you can continue to increase the silver at that point. It doesn't really matter. And all that solid that would come out would be the silver chloride. So by knowing the concentration of silver that's necessary to precipitate out both of those guys, you can selectively precipitate out one ion and leave the other one floating. And if you wanted to, then you could take out the other ion, and you can take them out basically one at a time, which is very advantage here. Because again, if you just willy-nilly just kind of grab some silver nitrate and dumped it in there at a concentration higher than 8 times 10 to the minus 9, everybody's going to come out, right? And you'd have no idea as to which one is which in this case. Any questions on that? So that's one of the nice sort of real life applications of KSP is you could actually use it to figure out the concentration you need, for example, to precipitate out an ion, to keep an ion in solution, and you can take advantage of that and use the appropriate amount of concentration to get those things to occur. Any questions on that there? Okay, so selective precipitation, KSP, is used a lot. And as I mentioned, it's used a lot really in these type of experiments, which are the qualitative analysis experiments. Qualitative analysis experiments are groups of ions, and there's group 1, group 2, group 3, group 4, group 5. These are not groups on the periodic table. They are actually groups based on solubility, so they have similar sort of solubility. So for example, you just think about solubility rules of chlorides, bromides, and iodides. They are soluble in everything except for silver, mercury 1, and lead 2. And we typically have a group precipitating reagent. So if we had something like hydrochloric acid, that chloride from the hydrochloric acid will cause all those guys to precipitate out as chlorides. That would leave, for example, if you had all these guys in there, it would leave all those guys still floating around in the solution. Then if you want to take out group 2, you could use hydrogen sulfide gas, which is very smelly. And that will precipitate out group 2. But if you look at group 3, it also uses H2S, which is the same reagent. The difference here is what we were talking about earlier. In group 2, it's really acidic, and really acidic, like 0.5 pH, really acidic. And because it's really acidic, that will allow only the group 2 guys to come out, but keep the group 3 guys still in the solution. And once you get the group 2 out, you can then turn it really, really basic, and then that will be the right condition for those guys to come out. So as we were talking about earlier, the pH can play a really big effect in terms of things precipitated out and not precipitating out. And when you do these type of experiments, that's where you kind of can use that to your advantage. At the end here, we typically will end up with guys that are soluble in everything like potassium, sodium, ammonium. There's like flame tests that you could do when you get to those guys that can help you out identify those things. Good news is we don't do any of those experiments here anymore, so that's also a really good news, I suppose. I used to teach at a lot of places, I still do that. That's all they do. If you only do that as the labs for this class was those type of experiments. You did nothing else. It was like months and months of add, precipitate, centrifuge, precipitate, precipitate. And a lot of those things are very not great chemicals and very smelly, most of those. Group 2, group 3, sulfur. Uh, so you should be very happy you don't do any of those things there in this place. Any questions on KSP? Then let's talk about the next equilibrium, which is KF. And KF is specifically for complex ions and complex ion formation. And a complex ion is typically a metal ion that has a bunch of what are referred to as and ligands are Lewis bases. And as you remember, when we talk about acid and bases in our favorite chapter ever, which is 14, Lewis bases are things that will donate a pair of electrons, right? So these are guys that will donate a pair of electrons. So remember that things that are good Lewis bases are things that have a negative charge, things that are polar to have some non-bonding electrons like water, ammonia, chloride, for example. So this is cobalt, and this is our ligand in this case. And we get this guy, which is a complex ion. And because it's an equilibrium, we could write an equilibrium expression for it, which is our products over our reactants. And just like normal, we do need to take things into account. And this equilibrium constant is what is known as KF, and it's sometimes referred to as the formation constant. It is the equilibrium constant for complex ion formation. Now, what we just saw with KSP is KSPs are really small values. KFs are really large values. So typically speaking, these are really large values that we have for KF. And what that means is we really do see that the formation of a complex ion is definitely favored, and products in this case is favored. So as we will see, whenever there's like an opportunity for a complex ion to form, it will actually form. And for example, as we were talking about sort of those qualitative analysis sort of experiments, one of the ways that you can determine if you have silver, for example, is you could add ammonia to it, which will make this complex ion. And when you add ammonia, it is strong enough in a sense to take your silver chloride, which is a solid, and pull those silver ions out of the chloride and into the complex ion, into the solution. So you could actually get your silver chloride to, in a sense, go away. And the silver ions hook up with the ammonia. You then can make it really acidic, and the ammonia will go away, and your silver chloride will come back. So the formation of a complex ion is usually always favored because they have really large K values. And whenever they have that opportunity, they definitely want that to occur. Now, when we see a KF value, like any other K value, it means that the higher the K value, the more stable the complex ion is. We would have more products, which is what we see here. Now, when we add ligands, by the way, they actually do come on one at a time. So they're kind of similar to hydrogens, how they come off basically one at a time. When we actually add the ligands, they come on one at a time. So for example, what we're seeing here is really the overall reaction that's happening. And the first thing that would happen is our cobalt will actually just add one chloride, and you would get something like CoCl plus. And there could be a K value for that expression. The next thing that would happen is that CoCl plus will pick up the next chloride, and we'll get CoCl2. And we also could have a K for that. And the next thing will happen is this guy here will pick up another chloride. we'll get COCl3 minus. And lastly, our COCl3 minus will pick up another chloride and we'll get COCl4 2 minus, and that would be K4 in this case. This is the stepwise equilibrium that occurs, and each of the steps as that sort of ligand comes on is an equilibrium step. That means that if I added all these guys together, that would cancel, that would cancel, that would cancel, and it would leave me with what we have up on top, which is the overall reaction that's happening. 1, 2, 3, 4 chlorides makes our complex ion here. And if I did not have the Kf value in this case, I would find it by doing what with all those individual ones? Do we add them? Do we multiply them? We do multiply them. You would multiply all those K values together, right? And that will give us our Kf value if you're not given it. So sometimes with these problems, as we will see, sometimes it'll give you the overall sort of end reaction that happens after all the ligands are attached. Sometimes they may give it to you in sort of a stepwise fashion. You can add them together, get the overall reaction, and multiply the K values together. Any questions on that there? I think we will lay it up there for today.